Okay, so I'll wait for people to join this meeting. We'll start at 3:05. Good evening, Karthik.
Good evening, sir.
We'll start in a while. Let's wait to see if more people will join this meeting or not.
Okay, sir.
Do you have any feedback about these classes? If you would like to me to improve upon something.
It's going well, sir.
Okay.
What
So
I thought,
you,
eh, yes, sir.
uh, your background is in mechanical, right?
Yes, sir, mechanic.
Okay. So have you gone through quantum mechanics earlier?
No,
Okay.
I've been doing the courses on this electronic materials and all those things from past
Mm-hmm.
1 year. Uh, both from IIT Madras only, so regarding the domain certification in electronic materials.
Okay.
Then,
Okay.
yes, okay.
Okay. So I will try to keep these questions like in a basic form. Uh, will as uncomplicated as possible. You can stop me if you have any questions anywhere.
Okay, sir.
We'll wait for 2 more minutes.
Yes.
Okay, let's start.
Yes, sir.
So, so this is the first question. This is the week 5, and this is the first question. A human body at room temperature gives out what kind of radiation? Visible, ultraviolet, infrared, or black?
Infrared.
Infrared. Yes, you're right. This is why we have this IR guns to measure the temperature of our body. So let's understand why it is infrared. So, so we know that heat is a form of energy And from, like, there is this theory by Planck. So Max Planck gave this theory that you can write energy as a it's proportional to the frequency, and introduced a constant which he like denoted by h, which later became the Planck's constant, into the frequency of the uh, wave. So, and heat is measured in temperatures. So we can say from this that temperature and frequency are correlated. So you can also write mu as
C by lambda.
c by lambda. So even temperature and wavelength are correlated. So this is why whenever, like, for whatever material is there, it has a it has a particular radiation, a frequency that is it is giving out. So it is known that if you draw, like, now which anybody can emit radiation, that intensity of this radiation is also mentioned as spectral radiance. It's nothing but the intensity of outcoming like ejected waves rays. Its unit is watt, which is the power, like, energy per unit time. This is a meter cube in the end, which comes from the per unit wavelength per unit area. And if, as a function of wavelength, it is seen that it follows the curve like this. Just the color. Now, so it's T1 and T2. It is seen that for uh, in this case T2 is always greater than T1. So this is experimentally observed, that we get this kind of a spectral radiance versus wavelength plot. And there were two laws that were given to explain this. The first is the Stefan
Volts.
Boltzmann law, which basically says that the intensity, where I is the intensity, is nothing but the area under this curve. Intensity is proportional to temperature to the power 4, or is given by a constant sigma into the proportionality constant t to the power 4. So as you increase the temperature, the area under the curve increases. So we see that for T2 greater than T1, the area under the curve is higher. And then there is the other Wien's displacement law. It's given that this is the lambda max for at T2. This is the lambda max at T1. So lambda max into temperature is approximately 2898 micrometer Kelvin. So this lambda max is refers to the most intense part of the spectrum. So this is like the most intense part of the spectrum, and this is the most intense part of the spectrum. So if it's let's say a human body, so human body is not a perfectly a black body, but let's take that assumption. if we try to find out what is the wavelength of a human body, so our normal body temperature is around 36 degrees centigrade. This is our normal body temperature. Which is like 273 plus 36, around 309 Kelvin. And so if you try to calculate lambda max, it comes to around how much? It comes to around 9.4 micrometer. So this lies in the infrared range. So this is why for measuring our temperatures, we have infrared sensors. We cannot measure it using normal photodetectors like UV or in the visible range, because our waves are in the infrared range.
Okay, sir.
Now, so this is a plot from which I found in the literature. So you can see that this is around. So this is 10 micrometer, the pinpoint range at this one. So we are in the infrared range. 9 micrometer is in the infrared range, and that is why we have IR sensors. And also, even in the visible range, we know that the frequency of red light, the frequency of red light is smaller than the frequency of the blue light. So as you increase the temperature, we see that the frequency of the frequency of ejected light is also increasing, or the lambda is decreasing in this direction. Lambda is decreasing in this direction. That is why also when we have flame, or when we have like any molten material, let's say we have a molten steel or molten iron in a blast furnace, it has a particular reddish orangish color, and just from the color we can sort of estimate what is the temperature of that material. And so I hope this is how we can calculate the color of emanating light from any material.
Yes,
Is this clear?
yes, sir. Yes, sir.
Okay. So the second question is similar to the first question.
That's what Wayne's displacement.
So what does this constant lambda max into T imply? So again, as I had mentioned, this is the
So as the lambda max increases, the temperature decreases.
which option is that?
D.
So you are saying option D. Wavelength corresponding to maximum intensity of radiation increases with decrease in temperature of an object. Yes, you're right. So we see here that as we decrease the temperature from T1 to T2, the lambda max increased. So we see this shift with a decrease in temperature. So the answer is D. So now match the statement with the equation that most directly corresponds to it. So there is this for the Wien's displacement law. This is the Wien's displacement law. This is the Stefan-Boltzmann law, and this is the Rayleigh-Jean equation.
Yeah. First is Stefan Boltzmann, I think. Sigma T to the power of 4. Capital A with small b.
Capital A, small b. Yes, sir, right.
The interaction between matter and radiation. EC 8 by kT by lambda 4. Yeah.
Yes. So B, C, and the other answer.
That's what wavelength corresponding to the maximum intensity decreases, and that's what Wayne's displacement.
Yes.
C
So
is
D is A. Yes. So the answer is A, B, B, C, D, A, B, B. Achha. So B is the answer of this question.
Yeah.
Now, if you would look at this equation, so this is the equation for intensity. So if let's say you decrease the lambda to a very small value, or that is, if you move to, let's say, a very high frequency regime, you see that the intensity shoots up.
Yes.
So this is, but if you see the experimental observation, you can see that with a decrease in wavelength, the intensity doesn't actually shoot up; it falls down. What I mean is, if I let me draw it here again. This is again the spectral radiance. This is the wavelength, and this is the experimentally observed. It's the experiment. And from the Rayleigh-Jeans equation, you can see that there is no term that is supposed to decrease this intensity at higher frequency regime. So this is the plot corresponding to this. You see that in this regime, the equation, this formula fails to explain what is happening, and this thing is called ultraviolet catastrophe.
It is a
Why?
Rayleigh-Jean equation.
Yes. Why would you call it ultraviolet? Because we decrease the wavelength. As you decrease the wavelength, so as you decrease the wavelength, you move from the infrared to visible to ultraviolet regime. And in the ultraviolet regime, this equation couldn't explain what is happening.
Okay.
So which is why this equation could not explain what is happening, and so further studies were done by Max Planck to explain this part of the curve. What is happening here? So Max Planck did further studies to explain this part.
Yes.
The universe's temperature is determined using the concept of which of these? Blackbody radiation, ultraviolet catastrophe, Planck's formula, energy exchange between the matter and radiation occurs in discrete shape sizes.
One is black body radiation. D also, I think, energy exchange between matter and
A is the answer. D is
D.
the answer.
Ultraviolet catastrophe is not there, but I have doubt with Planck's formula.
Okay, you have doubt with this one.
Yes, C.
Okay, let's discuss about it. So it has been found out. Do you know what is the temperature of the universe?
This 5,700 kelvin.
No. So that is in the hotter part of the universe, wherever there is sun and all. But where there is like no matter, so it has been found out that the average temperature of the universe it's 2.76 Kelvin. So this is like wherever. So there was initially this Big Bang, and when this and in a very small region there was a lot of energy, and slowly when this big bang happened, so the universe has started expanding and the universe started cooling down. So from the big bang till now, the universe temperature has cooled down till 2.76 kelvin. And so in the year, so this is this universe temperature that we're talking about here. This is 2.76 kelvin, and this was explained by Mather and Smoot. So they received the 2006 Nobel Prize. So you will see that I will take this term Nobel Prize a lot of talk about Nobel Prize a lot in this assignment, because a lot of these people did a lot of amazing work during the 1919, like early part of the 1900s.
Yes, sir.
So they got the Nobel 2000 Nobel Prize in physics for the discovery of this uh, the cosmic microwave background radiation, which explains through using which he found out the universe temperature. So their work was on discovery of the cosmic microwave background radiation. So this is why they received the Nobel Prize. And what this cost, so we can see CMBR. So what CMBR? Yes, it is the radiation released when the first atoms formed. So this is approximately, it is said to be around 380,000 years after the Big Bang. And so this is, and so we use this cosmic microwave background radiation and so this, it's a radiation, right? So radiation has a wavelength. It's a wave. So they use this they studied the wavelength of the radiation, and then they again, like as we saw in the Wien's displacement law, or in this case the Planck formula. If you look at this formula, so this so this pi is a constant, Boltzmann's k is a constant, Boltzmann constant. So Planck's constant is the h, c is the speed of light. So there are only two variables, temperature and wavelength. So the temperature and the wavelength are related. So if you know the this value was found experimentally, this value was found experimentally, and so the temperature could be found. And so that is how, by calculating the lambda of the radiation, they were able to find out the temperature of the universe. So along with so black body radiation energy exchange, also the C is an answer, because this is the formula that they use to calculate the temperature using the wavelength.
Okay, sir.
So both so all three, A, C, and D are the answers to this question.
Okay. So in that formula, that 8 pi kT, so kT repeated twice now, that Boltzmann constant and the temperature. Again in the exponential also it's repeated.
Yes, yes, yes. Uh, we need not go to the exact derivation of this formula. It's a little bit complicated, but we can just see that there are only two variables: temperature and lambda. So everything else is a constant. So if you know one, you can find the other thing.
Yes.
So it's a little bit complicated derivation also. That's why I'm skipping the derivation in this uh, class. So we talk about the religion score relationship earlier. So and there's also this Planck's derivation of for explaining this the radiance versus wavelength plot. So we have this plot. Sorry, we have this plot. So there's a religion equation to explain this, and there's a Planck's equation to explain this. So the question is,
The higher temperatures.
uh,
Higher
so
wavelength.
yes, yes. So what is the answer?
It's true.
So yes, they coincide at higher wavelengths. Yeah, at larger wavelengths. Yes, sir. Right. So let us discuss a bit about the Planck's model. So this is the same Max Planck. So the Planck's model. So what he said is that any black body constitutes of oscillators. Oscillators are nothing but like a spring mass system. Basically, you have two masses or a ball and a mass, and then you have a spring in between. And so, if you like apply some kind of force in one direction and you leave it, it will keep oscillating. So his assumption was that black body constitutes of oscillators. It's an assumption, and then he arbitrarily arbitrarily assumed that to activate an oscillator of frequency given by mu, the energy that is required is proportional to the frequency mu. So this is where we got that equation E is equal to h nu, because it says that energy required is proportional to the frequency and h is the Planck's constant. So now if the frequency is then higher, so an oscillator of a higher frequency will require more energy to get activated. So higher energy is required to activate an oscillator of higher frequency. Okay, this is understood till now, right?
Yes.
Okay, now what happens if the energy in the system is constant, is finite? For finite energy in system, so as the frequency increases, or as the as you go like find oscillators of higher and higher frequency, it becomes, so it becomes less likely that the oscillator will be activated. So what happens? Let's say you have a fixed energy, and that energy is insufficient to activate that oscillator. If the energy required by the oscillator is lesser than the applied frequency, then it can activate. But if it requires more than the applied energy, then it cannot be activated. So there will be a certain point after which it will be impossible to activate such oscillators. Less likely to impossible. So this happens as the frequency is increasing. So eventually it's like impossible to activate such oscillators. And so what will happen? Such oscillators will be switched off. So because it becomes impossible to supply so much energy, such oscillators will not be activated at all. So what it means is such frequencies of radiations of such frequency will not be emanated or ejected from the black body at all. And so that is why what happens is that at very high frequency, it drops to zero, and then it starts increasing. Because if you plot energy increases in this direction. So for very low wavelengths, it becomes almost impossible to, this is the intensity or spectral radiance. It becomes impossible to activate those oscillators. Whereas at lower wavelength, that is at lower frequency, that is at higher wavelength, the energy decreases, right? The h nu. The energy required to activate the oscillator, which is like h nu, is low. And so these oscillators will be readily activated with supplying energy. So which is why you will get, so now we have a plot like this. And so this was also, okay, I'll just plot it. So from this Planck's law, see that at low temperature they'll be readily activated. Will be readily activated. This is also like seen by the Rayleigh-Jeans equation, that even in that case it's like readily activated. But this the Rayleigh-Jeans equation cannot explain what is happening in the case of low wavelength regime. Whereas in the case of Planck's model, we see that it's an oscillator model. It shows that at lower wavelengths, the radiation stops emanating because the oscillators are not activated, and that is why only at higher wavelengths both of these follow each other. At lower wavelength, the Rayleigh-Jeans relation fails. So only at higher wavelengths they coincide, the Rayleigh-Jeans and the Planck's model.
Yes.
So just for reference to the online students, spectral radiance, and this is the wavelength. So you can see that just by one plot of black body radiation, to explain this plot, so many people have worked so hard, and it led to the eventual coming out of the quantum theory.
Yes.
So who showed that electromagnetic radiation or light has a dual nature?
That is Einstein.
Yes, the answer is Einstein. So, in 1921, he received the Einstein received the Nobel Prize in physics. In physics for the why? For the discovery of photoelectric effect, and also because of his contribution to the quantum theory. So he first of all he borrowed the idea from Planck. So he borrowed the idea that energy is given by Planck's constant into frequency. So he borrowed this idea from Max Planck. So Planck, to explain the black body radiation, he came out with this formula, and so Einstein further carried forward this formula to explain his the observation of photoelectric effect. So first of all, he showed that a minimum threshold energy is required to eject electrons. So this effect can be observed. So the photoelectric effect occurs only when the h nu, which is like the incoming photons energy, is greater than the work function of the material. So if it is lower than this work function, then no amount of so then no electrons will be ejected. So and even if let's say if let's say even if at low intensities, if h nu is greater than 5, then photoelectric effect seen. But even if intensity is high, but the applied energy is lesser than the work function, then photoelectric effect is not observed. So he showed that the intensity of light doesn't matter. It just determines how many of these electrons will come out. But whether an electron will come out or not depends on the energy of the depends upon the energy of the frequency of the incoming light.
Now, this work function means the level above the conduction band.
Work function is basically how much energy you require to make an electron truly free. So in any material, if electron is there, it will be bound to that material. If you have to take it, if you take it to infinite distance, then it will be completely free. So how much energy you require?
1 second, 1 second.
Hello. So it is how much energy you require to move this electron from the material to an infinite distance where it does not experience any kind of a potential.
Okay,
That is the work function. And then thirdly, he said that this when we provide excess energy to the system, which compared to the work function, then the extra energy becomes transforms into the kinetic energy of the emitted photoelectron.
Yes.
So this delta energy that is left out, it becomes the kinetic energy. So if you increase the frequency, then the delta E also increases, and so the kinetic energy also increases. So this is what he observed, and he wrote down this all of this in the form of his equation. This kinetic energy is half mv square is given by h mu minus phi.
Fine.
So this is the equation that he put forward. Now let's discuss about it. So here what we see that the energy of each photon is important. So energy of each photon is important for emission. The intensity doesn't matter. So what this means is that, let's say there's a oscillator which has to get activated, and it needs certain energy, and this energy, uh, uh, let's say how to say, let's say this is an oscillator, and it requires a certain energy to get activated. If the energy is lower than this activation energy, then it won't get activated, and if it is higher than this, then it will get activated. But no matter, even if the energy incident is, the photon energy is very low, but the intensity is very high, it won't get activated. So what this means is that the energy of each photon is important, and it comes in pulses. It's not a continuous thing. If it was continuous, then even the intensity will matter. But in this case, the intensity didn't matter. So what means that energy was coming in the form of pulses, in the form of particles. So that's how he showed that that light is a particle, and he stuck to this idea that light is a particle, and so that is how he showed that is in photoelectric effect, that the particle behavior of light. And then earlier it was already known that light is a wave by uh, this in Young's double slit experiment, that light can interfere and the light can diffract. So by showing that both it's a wave and a particle, that was done by Einstein for the first time. So answer is B.
Yes. Surface of heating, and then
Electrons are released from a metal surface on heating, and these electrons were incident on a nickel sample to see diffraction pattern. What does it show?
theory. A, B, D.
Okay, so we will discuss about it. So let's study the history of how this all happened.
Okay.
So let's go one by one. So in the first, so the Newton, the Sir Isaac Newton gave the corpuscular theory of light. So what are corpuscles? They are like the small and extremely light. By light, I mean in terms of like mass. light particles.
Okay.
So he said that basically that light is particle. And then in the year 1801, the Young showed the double slit experiment, which in which he showed that light uh, interferes and diffracts, which shows that light is a wave, which contradicted the Newton's theory. And so it was established at this point. So at this point, it was established that light is a wave. Then what happened? In the year 1887, Hertz. So Heinrich Hertz, on whom the term the 1/second, which is the unit of frequency, was named after, Hertz. He discovered the photoelectric effect. He observed it for the first time, and then in the year 1905, Einstein explained the photoelectric effect. So again at this point, they show that light is a particle. Now there is a now there uh, now there were like two contradicting views, whether light is a wave or light is a particle. So again in the year 1924, Louis de Broglie, he said that all matter has wave property. And so what he did is that he wrote the equations for the energy, which is going to mc square from Einstein, and equated to the energy value given by Planck is equal to h mu, and he showed that the lambda, the wavelength, can be written as h by p, where p is the momentum, mass into velocity. So c was the speed of light in this case. So this here is showed. So he gave the theory: light is both wave and particle, which was called the dual nature.
Dual nature.
And this was a theory. Then what happened? Well, this was in 1924. Then again in 1927, Davison, Kramer. So then Davison and Kramer, they performed this experiment. This was done by Davison and Kramer. So they saw that when these electrons were incident on nickel sample, they could see diffraction pattern. So on heating, electrons are generated, so like particles, and then they see a diffraction pattern, which is a property of wave. So in 1927, Davidson and Kramer, they experimentally, so they found that electrons can diffract. So they experimentally they showed that, demonstrated that actually, demonstrated that in this case electrons are both wave and a particle. So now we can start answering this question. So this is so they saw that it shows the wave particle duality.
All of the options.
So it was done by Davison and Kramer. So it was confirmed the de Broglie theory, and it also shows that a particle can behave as a wave at the same time. So all the
Yes.
options are correct.
Okay.
So okay, I hope it's clear.
Yes, sir. So, but Davison-Kramer's experiment, was it
Mhm.
done before the invention of this X-rays or after that?
Uh, okay, I do not know where when the X-rays were discovered by Röntgen, or also more like when XRD was performed. But you are right. Like this is similar to the X-ray diffraction.
Yes, sir. That's why.
This is similar to X-ray diffraction, like as observed in as like when light X-rays fall on crystalline materials.
Yes.
So even actually X-ray diffraction is a so if you so we will be discussing about X-ray diffraction in our, I think, probably next tutorial or the next to next tutorial. So then we have something called reciprocal space, which is also a very interesting concept.
Yes.
And then we see that the real space and the reciprocal space are correlated together by the Bragg's law. But okay, that's the thing for the next class. We'll discuss it in the next or next to next class. So the Schrodinger equation is a equation derived using nuclear energy of the particle, fundamental equation that looks at the sum of kinetic energy and potential energy. It's a derived equation using only the kinetic energy of the system while eliminating the potential energy of the system.
Schrodinger equation. I think B. Huh? B. Sum of kinetic and potential energy.
Yes. So there's sum of kinetic and potential energy. So uh, I will come back to this equation in the end. Okay, I will write down the equation here. So I wanted to uh, show the time dependent and the time independent wave functions, solutions of the Schrodinger equation. So we know that the Schrodinger equation is written by h cross square by 2m d2 psi, so the function of space and time, by dx square. Then there is a potential term which is again a space and time dependent operator. It's a operator. So this is the fundamental equation. Both so this is both space and time dependent. So what does the solution to this equation give? Describes the trajectory of a quantum particle in a probabilistic manner, which is in the next questions, which is also discussed in the next question. According to the Born interpretation. This is a scientist named Max Born. So when you are solving this equation, this fundamental equation that looks into the sum of kinetic and the potential energy, once you solve it, you will get a solution for the psi. So and the meaning and with the Born interpretation, you can use psi to find out what is the probability of finding this particle, a quantum particle in a particular space, in a particular space. What is the probability? So that is what you can find out by solving the Schrodinger equation. And so if also there are like more nuances. So if there is no potential that is applied, so these are operators, and it's sort of like the kinetic energy operator in the first side, and then this is a potential energy operator. And so if there is no applied potential to the particle, then this becomes zero. If the particle is free, which is, what it means is that moves under no force. In that case, the second term will become zero. So it's a fundamental equation. It cannot be derived from a more like it cannot be derived. It's just as it is. There's no derivation for the Schrodinger's equation. If we don't have enough time, else I would have discussed more about this Schrodinger's equation. Okay, so then we come to the ninth question. Product of a wave function in its complex conjugate helps in determining the probability of finding a particle in a region.
Wave function.
Okay, so this is the Born interpretation, which I spoke about in this previous question, about determine the probability of finding the particle.
Okay.
So the Born interpretation, for which he got the 1954 Nobel Prize, so it was given to Max Born. So he interpreted, so Born interpretation of the wave function psi. So we write this psi here, right? So he explained, so this like what this psi means. Before that, we did not understand like what is the physical significance of this psi. And with the Born interpretation, he explained what is the meaning of this psi.
Okay.
And he said that if psi star is the complex conjugate of psi, then psi star dx, or you can also write it as psi modulus square dx, is the probability of finding the electron between x and x plus dx. So this is in like only in one dimension. Let's say I'm discussing only about x. Even this equation is for only one dimension. It's only in one dimension, and so this is the uh, so this is how Max Born gave the interpreted the meaning of the wave function psi. So what is the answer? That's true.
True.
So then we come to the last question. So,
Heisenberg.
so which of this is the Heisenberg uncertainty principle?
A, option A.
Just this option A. So again, Heisenberg uncertainty is like uh, usually like we are said so in the school level that it's an experimental limitation, but it is not so. It's a fundamental limitation. Not an experimental limitation. So and why does this exist? Because this exists because everything in the universe behaves both as a particle and a wave at the same time, which is given by Louis de Broglie. So this is observed. This fundamental limitation is observed because like everything, like all materials, all matter behave both as a particle and a wave at the same time. And so we don't have the time. So I'll not ask you to solve. I'll just give some values. So let's say you have a cricket ball of like 100-gram mass with a velocity of 40 meter per second and a like delta p of 1%. So what we will find out is that from this, if you apply this equation, the error in the position is in the order of 10 power minus 33 meters, which is like which we cannot observe. It's a very small value. So in this case, we cannot observe the effect of uncertainty. Whereas if you let's say take an electron, it has a very small mass, right? It has a 9.1 into 10 power minus 29 kg. And then for the same velocity and for the same uncertainty in the momentum, we see that the delta x comes to around 10 power 6 angstroms, which is like a very large value. So the lattice parameters around like if for materials will be less than 1 nanometer, will less than 10 angstroms. It's a very large value.
Yes.
So this uncertainty, uh, this uncertainty is enormous in the microscopic world. in a microscopic world. So you can see that because of the change in mass, the uncertainty increases by so times. So obviously that the velocity of electrons are not so low. We studied about this earlier when we were talking about the Drude model,
Yes.
that it's around 10 power 5 and it's not 40. So this uncertainty will be less, but it still becomes very important for electrons because of its very low mass.
Yes.
So the answer is A. Okay, so I hope you understood the questions in this class.
Yes, sir. Very much.
Okay. So it's the time is up. If you have any questions or if others have any questions, they can put it up in the discussion forum on the NPTEL website, and we can stop here.
Yeah, yes, sir.
Okay.
Yes.
Thank you. Thank you for joining the class. We'll stop it here.
Yes, sir. Thank you.
Thank you.